Ladies and gentlemen, I'm John Pethiker, the Physical Sciences Secretary and Vice President of the Royal Society, and it's my pleasure to welcome you here to the Royal Society and the Bakerian Lecture. This is the Society's 351st year, some of you will have noticed, but also it's the Bakerian Lecture's 236th year. Now, before we get on to the lecture, I've got some nuts and bolts things here to say, including if you have a cell phone, please switch it off. The event is being recorded live, and I've just been told that it will be available on demand at royalsociety.tv. We were hoping to have a live webcast, but as you may have heard earlier today, there are various kinds of power cuts here, and there's been a certain amount of excitement with the IT system, so we're not doing it live. Okay, so if all the cell phones are turned off, then a brief introduction to the lecture. The Bakerian Lecture, it's the Society's premier lecture in the physical sciences, and it originated in 1775 through a bequest by Mr. Henry Baker, a Fellow of the Society, of £100 for an oration or discourse which was to be spoken or read yearly by one of the Fellows of the Society on such part of natural history or experimental philosophy at such time and in such manner as the President and Council of the Society shall order and appoint. Well, this year's lecturer is Herbert Huppert, who is Director of the Institute of Theoretical Geophysics at the University of Cambridge. He hails, in fact, from Sydney in Australia with his youth and education in the early stages. He then graduated in applied maths from Sydney University and with a university medal, travelling fellowship and many other awards. He completed a PhD at the University of California, San Diego, and then came as an ICI postdoctoral fellow to Cambridge in 1968 for what was meant to be a one-year sojourn. He hasn't left yet. Now, Herbert has published very widely in fluid mechanics and many other subjects, and he's asked me not to go on at great length about that because you'll hear from him directly. He was elected a Fellow of this Society in 1987 and has received numerous awards. I'll just mention one here in 2005, was awarded the Arthur L. Day Prize Lectureship of the US National Academy for contributions to earth sciences, and was in fact the first Australian to win this prize. Again, he has numerous other awards, and therefore it's my great pleasure to present Professor Herbert Huppert, the 2011 Bakerian Lecture.
Well, thank you very much, John, for those kind words, and thank you also for keeping it short. And thank you all for coming. I'd like to also thank the President and the Council and the Awards Committee for recognising me in this prize. I'm sure they had many wonderful candidates, and I really felt most honoured. After the shock and surprise had worn off a little bit, I wondered at what level was this lecture to be spoken or read to be delivered. And so I called a friend of mine who'd won the prize a few years previously and said, "How did you pitch the talk?" And she said to me, "Well, it was rather difficult because sitting in the front row was my mother, who left school at 15. And sitting next to her was the then President, Martin Rees, who knows an enormous amount about my field of research." So I said, "Well, what did you do?" And she said, "I spoke to my mother." Well, my mother died some years ago, so I can't speak to my mother, but what I would like to do is to give a lecture which gives you some indication of the subject at the beginning, and I'll start with an introduction and motivation, and then tell you something about the storage of carbon dioxide underground, which I believe is a very important aspect that we must follow, and also from which we can make a lot of money, and that these days is important. I'll tell you then, with a little bit of mathematics, I'll try and keep that short, about dissolution, how you might make that sequestration of carbon dioxide safer. On the other hand, I'll tell you about leakage, and I'll do some experiments, as you'll see here, and I'll show you a leakage experiment. And I'll tell you something with another experiment about heterogeneous permeability, and then I'll tell you about conclusions. Now, 13.7 billion years ago, roughly, there was a big bang, and our universe was created to look something like this. And let me make it clear, this is real size at the early beginnings. Then this asymmetry, got pieces of matter together, and then Newton's law of gravitation brought more matter together. And about 4.5 billion years ago, the Earth was formed. It's evolved over those 4.5 billion years, changed quite considerably, and leads to the state that we see it today with oceans and atmosphere and clouds and the continent. This is a composite photograph. Could we turn these lights off a little bit, please? Thank you. This is a composite it's these, the front ones. This is a composite photograph of the Earth at night, and it's a proxy, a rough proxy of the population. You see that there's a large population here in Eastern North America and over Europe. Just about 120 or 130 years ago, the similar photograph would have been like that. And you really do need to turn the lights off for this. Now, in the last few decades, we've really got enormously sophisticated in our culture and in our ability to make quite remarkable things, but a lot of that depends upon oil and the burning of oil and other fossil fuels. This is a graph of the ratio in the last 100 years of the world population, the United States population, and world energy usage and US energy usage. I'd have loved to have put on the energy usage of either China or India, but I couldn't find the value for the energy usage in the early 1900s, and I suspect it would have gone pretty close to the mathematician's dread of having to divide by something that's close to zero. However, what I can tell you is that today the energy usage of the US and China are comparable, and just 10 years ago China used half the energy that the US used. So there's been that rapid increase. And now this is not sustainable. We have a finite Earth, and these increases are really just not going to be sustainable unless we change things. To give you another indication, this is a graph of the number of cars in millions as a function of time. There's something like 700 million cars in the world today. There's something like just over 250 million cars in the United States. So that means that on average, every single person in the US has a car. The 10-year-olds and 15-year-olds, they on average own a car, even the 2-year-olds. Well, that also is increasing, as you see, quite considerably. For comparison, in the 1900s, there were 8,000 cars in the US. There were 144 miles of paved roads in the whole US, absolutely nothing in California. Most of our energy comes from the burning of fossil fuels, coal, oil, gas. There's very little in nuclear, and my belief is that unfortunately, because of the nuclear problems in Japan, nuclear will be even less on the subject matter in the next few decades, and very little of anything else. This is a photograph that was given to me by Ron Oxborough. It's actually in black and white. It's taken in China, where this coal-burning locomotive is dragging something like 100 wagons full of coal being taken somewhere to be burnt. Now, Tyndall was one of the first people to really ask the question of how warm should the Earth be? Why is it at the temperature that we more or less enjoy, though there are some cold spots and hot spots? Why isn't it 40 degrees warmer, 40 degrees colder? He knew about greenhouses and greenhouse effects, and so he decided to work at the Royal Institution on whether the atmosphere could be behaving like a greenhouse. And he did some experiments on different gases, and in particular he started quite sensibly with nitrogen and oxygen, because they make up most of the atmosphere, and he found they were not greenhouse gases. They didn't trap the radiation. He was about to give up the investigation when he thought, what about those aspects in the atmosphere that are rather minor, carbon dioxide, water, and methane? And he found that they were, of course, very small. He knew that, but they have very powerful effects. Now, in some sense, the subject, or the recent part of the subject, started, and I think there's an important story here, when Dave Keeling, who came to Scripps to do a postdoc, and he didn't know quite what he wanted to do, and he thought it would be nice to go to Hawaii. What could he do in Hawaii? Well, he could measure the carbon dioxide in the atmosphere, and Roger Revelle, who was paying for him, couldn't see why not to let him have a good time in Hawaii. So he went and he started the measurement of carbon dioxide in the atmosphere. And what we see here is that there are the seasonal trends as the carbon dioxide is taken up by the leaves in the trees and then given up as it dies. But there has been, on average, a steady increase from about 310 to 390 parts per million over just 50 years. And what I find nice is that Dave Keeling's son has contributed the last bit of that. Now, at the same time, over the last 150 years, there has been a variation in the average temperature, the globally average temperature, an extremely noisy record, but I think it's quite clear that it has been increasing. Not everywhere. There are bits here where it's more or less uniform, except for the oscillation. The average is uniform, but in general, it has been increasing. This is now data for the last 1,000 years, showing first the temperature change, very noisy, but it has been increasing considerably over the last 100 years or so. The carbon dioxide concentration in the atmosphere, which has been increasing again, and the carbon emissions. And the important point is that we know from isotopic evidence that this is carbon dioxide that comes from the burning of fossil fuels, not from natural events. This is now a graph of the extent of the northern polar ice. And I've cheated a little bit because I haven't put in the last 2 years where it's up here, so it has gone back up again. But you see that in general it is going down. Things are definitely changing. Not everywhere. Here there's on average not been much of a change in the sea ice extent. Here it's been even going up for those few years. But overall, I think it's quite clear that things are going down. It's very important to distinguish short-term and longer-term trends. If we look at Antarctic glaciers, there's no doubt that there's some that are advancing, suggesting it's getting colder, but most are retreating, suggesting that it's getting warmer. Now, everything that I've told you so far is data from the past. What I want to do now is to present some data from the IPCC report, which predicts what the temperature might be in the future. There's nothing as difficult to predict as the future. And this is shown in this graph where the whole series of possibilities, and it depends a lot on us, what we do politically and with our carbon dioxide content. It also depends on how the atmosphere might react, because we're taking it into a region, especially up here, that is outside our experience. Why do we care that the mean temperature might go up a few degrees? In some places it may be advantageous, but in general it means a rise in the level of the oceans. It means that the energy contained in the oceans is larger, and hence there can be more storms at sea, there'll be more floods, more rain. In general, we believe that increases, especially as high as this, will be very deleterious. People sometimes say we must save the Earth. And what is not always totally understood is the Earth is totally safe. It's going to be around for another 13 billion years or so. What's important is to save the people on the Earth. And so comments that are made which say that 10 million years ago the Earth was also in the situation that we're getting towards is irrelevant because there weren't people on the Earth, and it's the people that we really care about. The Earth doesn't care less whether the height of the oceans is another even 100 meters, but for the people living in Bangladesh or in New York, that really is important. As I've said, fossil fuels supply 85% of the world's energy. We put out at the moment 28 billion tons of carbon dioxide per year. United States, China put out 6. Australia puts out rather little over Australia. If you count all the coal that's sold to Asia and elsewhere, this increases by a factor of about 8. On the other hand, the mean per person, Australia wins. I was born in Sydney, you remember, and it gets down as low as 0.1 in Nepal, and that might not be the very lowest value. But the important point I think to make here is a typical Australian says, well, look, we're 20 times less than China. It really doesn't matter much. On the other hand, the Premier of New South Wales said that if we stopped shipping coal and making money from that, our whole financial infrastructure would fall to the ground, and New South Wales, the state of New South Wales, might as well float over the Pacific. I thought that was an interesting idea of plate tectonics, that New South Wales could float over the Pacific, but there it is. Now, what are we going to do about this? Well, one possibility is to change our habits, to stop using as much fossil fuels, to going on bikes, to not catching planes, etc., etc. Now, that's an area that I'm going to leave, with all respect to my wife, who's a professor of psychology, but I don't think it's possible. We'll change by a little bit, but I don't think we're going to make drastic reductions. We're not going to bring 28 billion tonnes down to what we'd like to see, which is something like 14 billion tonnes at a maximum. So the other thing that's possible, and what I want to talk about today, is to store the carbon dioxide. Admit that we're going to put out 28 billion tonnes, and that will probably rise. How could we store it? There are a number of possibilities. One is to store it in ecosystems, i.e. to take into account those oscillations we saw, to have trees. And I read somewhere that in order to just store the carbon dioxide that comes from the power plants of Great Britain, you'd have to have half of England covered in forests. Now, that might be nice from one point of view, but I think that's rather unrealistic. Another possibility is to put the carbon dioxide in the bottom of the oceans. There are two problems that I see there. First of all, there will be acidification of the oceans, and that's already happening a little bit, as some of the carbon dioxide that we put into the atmosphere is dissolved in the oceans, and that dissolves coral and causes lots of problems. The other problem is that many places where carbon dioxide is formed are a long way from the ocean. The middle of the United States, for example, or the middle of Europe would have a long journey to be able to store it there. Another possibility is depleted oil reservoirs, where the oil has been taken out and we put in carbon dioxide. Another is brown coal seams where the quality of the coal is not sufficient to be worthwhile mining. Another possibility is mineralization. A lot of the Earth does consist of calcium carbonate, but of course the Earth has had, as I said, 4.5 billion years to do this mineralization. We don't have that amount of time. The most favoured possibility is into saline aquifers. large reservoirs of porous rock, rather loosely consolidated sand that are full of salty water, and we will push the carbon dioxide in. This has already been done for quite some time, since 1996, at Sleipner, where they take out natural gas, which has something like 15% carbon dioxide. They strip it via chemical means of the carbon dioxide, and then the idea was to put it back into this Atzera formation that is about 200 meters high. The carbon dioxide is released at the bottom of the formation. It's less dense than the surrounding salty water, and hence it would rise. It would rise until it came to some rock formation that would hold it, to which it would be impermeable, and then it would propagate as what's known as a gravity current, because this is relatively light fluid propagating out over heavy fluid. Now, gravity currents occur frequently whenever you have fluid of one density displacing fluid of a different density. And one of the experiments I thought I'd show you that you might like to see is, could we turn, oh, I turn the slides off, don't I? I have here some syrup, and I'm just going to put it on this plate, and you see I do it very carefully. And it spreads. Quite quickly it gets, maybe I'll put a bit more on. Quite quickly it gets into a rather circular shape. And the mathematics that we use to determine how quickly it propagates takes advantage of that fact. So this is a gravity current, a very simple gravity current, honey on toast. But what I'd like to do is to show you another experiment, which is to press it out. And you see it's now expanding and becoming really very circular under that weight. This is no longer a gravity current, it's being forced by this. Now the question is, what if we do the exact opposite? What if we lift these plates? Well, there's a theory in fluid mechanics that says when the flow is very sticky like this, if you reverse something that has made the flow, then the flow itself reverses. So what that means is if I lift this up, it should reverse in a nice axisymmetric way. And in fact, if I hold this up here, it should come right back into the container. Let's see how that will work. I need an assistant here to hold it. That part will leave. Let's see what happens. Quite a different structure. Very quickly goes to being symmetric when it's going in one direction. When it's less viscous fluid, pushing more viscous fluid, more sticky, then it becomes quite complicated. And that's an important aspect that we need to take into account. This idea of putting carbon dioxide has been used in Sala, in Algeria. And what I want to tell you now for the next 25 minutes or so is some of the theory and laboratory experimentation, and I'll show you some of the experiments, and the interpretation of field data. I'll just touch on some of the things that we've been doing. There are a number of competing phenomena. First, there's trapping. You want to keep the carbon dioxide down there. There's structural trapping due to the impermeable layers. There's capillary trapping due to surface tension, which I'll tell you something about in a moment. There's dissolution trapping, which I'll also tell you about in a moment, and mineralization, which, as I say, is too slow. Then there are competing effects. There's leakage. It's the exact opposite to trapping. Aspects that I can't talk about, but I'd like to mention here is what happens to this salty water in the far field. If we push carbon dioxide into the reservoir and that results in the salty water going into our drinking water, that's not a very good idea. And then finally, the question is when we put carbon dioxide at depth depth into the Earth, how much will the structural uplift be? It's not going to be good if there are many tens of meters of uplift in the surrounding countryside. Now, this is a graph of the density of carbon dioxide, or if you like, the volume for a given mass as a function of depth. As you put it down more and more, it gets compressed, and we want to store it in a compressed state because it takes up less space. And there's a depth of about 800 meters below which it behaves like a supercritical fluid. The fluid part is important. You've compressed it so much that it's no longer a gas, but behaves like a liquid. Now, what actually happened in Sleipner, and we see here, it wasn't exactly as they imagined. It didn't go up and act as a gravity current across this seal, but there were some thin shale layers, 10 centimeters to a meter in depth or so, that trapped the carbon dioxide, the liquid-like carbon dioxide, for a while, and then it seeped through at special places and then went up again. And there were a whole series of gravity currents. And this is where I became interested, and I apologize for the mathematics. This is where some of you can text your friends saying, I hope that you're at an interesting lecture. I became interested in this with a wonderful undergraduate student, Sarah Lyle, and we asked, what would be the form of the gravity current that's going like this, the top of a seal, whether it's a permanent seal or a partial seal, in a porous medium? And one writes down the equations. That takes you 5 minutes maybe to get the right equation, and then you can use this fact that it will appear very axisymmetric, just as I showed you, to work out that the radius goes like time to the half. And you can evaluate what the pre-multiplicative constants are given the input parameters. You can also work out the shape of this current, and it's almost linear, and it has no variation with time at the origin. Well, to do this sort of analysis doesn't take very much time, but what people had done is a huge computer program that took many years of work, and then they got these results, but they didn't quite understand what it meant. We then did some laboratory experiments and found that it agreed very well with this variation with time, and also this linear shape without any variation with time at the origin here. Recently, a student of mine, who I believe is in the audience, has looked at the effect of surface tension. What happens then when you have a two-phase system is you don't get a uniform value of the carbon dioxide, but there's a saturation because of surface tension that changes with time. Now, I'd like to show you an experiment which shows you how important surface tension can be. Would you believe it? It worked perfectly before. Thank you. I have some heavy fluid here. There's a gate here which stops the fluid running out. These are a porous medium, some balls here. And this is, as we'll see definitely later, a heavy blue-dyed fluid. And this is the most exciting experiment. You must look very carefully. I remove the gate, and nothing happens. Did you see that? The surface tension effect here is such that it can hold this heavy fluid against the air, just to prove to you that in actual fact this is a heavy fluid, and if I have more of it, so that the overpressure is greater than the surface tension. So it's exactly the same fluid as you saw. I now lift it up and away it goes. And this will slowly drain out. And this now, if you put it upside down, is just like a gravity current. And it doesn't make any difference whether gravity is going down or up. It will behave exactly in the same way. Anyhow, we could analyze that situation. We also found, thank you. We can analyze that situation, also found that it goes like time to the half, and applied this to some data that we got from Sleipner. The idea is you plot the square of the radius as a function of time at those various horizons, and then you see if you can get a straight line that fits those data points and brings it down to 0, indicating that horizon 2 already had some carbon dioxide right at the beginning of the experiment, 1996. Horizon 3, the same thing. Horizon 4 north, which took longer to get the carbon dioxide, as you see here. There's a third data point which has just been missed out here, but there's a straight line, and it takes 3 years before the carbon dioxide reached there. Horizon 8, it took 1 year for it to get there. This is the initial data. Some of the recent data, which I'm not allowed to show yet, doesn't show as perfect a agreement, but we believe what happens is that the carbon dioxide has seeped through these relatively thin layers. Now, what I'd like to say a little bit about is some work on dissolution, which comes about because you can dissolve some salty water in the carbon dioxide. Not very much, up to 3%. You can dissolve it in the carbon dioxide, and the resultant fluid is heavier than either the salty water or the carbon dioxide. And we can model that in the laboratory by using this special fluid that I started to use some 20 years ago, which is methanol plus ethylene glycol. And it has that same effect that as it mixes with water, you get a density that is non-linear, and there are some bits that are heavier, and hence what that means is you can put some relatively light MEG, a layer of MEG, above water, and it'll mix, form a heavy solution, and fall down. And here's a laboratory experiment that shows how that works. So the idea is you've got carbon dioxide stored at the top here. It mixes in with the water, produces these heavy plumes, and they fall down. Once they fall down, it's safe. You're not going to have any further problems. So that's an experiment. We can also do some theory, and if I just show you the result of the theory, basically it says that the velocity goes like the 4/5 power of the forcing, which is known as the Rayleigh number, i.e. the concentration difference. And here's the numerical results, and here are the experimental results, all of which lie on this 4/5 line. Why is that important? Well, we could then apply it to Sleipner and know the various parameters, what the permeability is, the height of the layer, the density difference, the viscosity, and work out from that, from our theory and experiment, that there should be dissolution at the rate of something like 18 kilograms square meter squared per year. Knowing what the area is, it says that about 1/10 of a million tons per year can be safely and stably stored this way. We're putting in about 1 million ton a year, so 1/10 of it is stored safely. If we stopped putting it in after 1 year, that would mean after 10 years, using a rather simple linearization, it would all be stored safely. But of course what happens is we're continuing to put it in, and it's only taking of the order of 1/10 of a million tons away this way. So this is a process that is very important, that works, but it takes some time. The opposite is to talk about leakage. And I've shown you a diagram here where the carbon dioxide spreads like a gravity current. It then comes to some sort of fracture and it leaks out of that fracture. Now it may leak all the way to the surface, which would be a problem, or it may just leak until it finds another seal on top here. I'd like to show you an experiment, what that looks like. Oh, I'm sorry if it's in somebody's eyes. Can I? Nothing much I can do, I'm afraid. Oh, I can do that. Right. So here I have some blue carbon dioxide, you can imagine, that's going to, thank you very much, that's I'm going to release. And you'll see another example of a gravity current. Very symmetrical, same down and up. And then it's going to come to this fracture. Some of it falls down in the fracture. And some of it keeps on flowing. I showed this experiment once to the director of research of a company, which I'm afraid I can't mention here, or they'd sue the Royal Society, no doubt, or sue me, even worse. And he said to me, this is about a year ago, but what if we plug off this leak? And I said, well, if you plug off this leak, then there's no more leakage. And he said, my company knows how to stop any leak, and quite quickly. I didn't quite know what to say to him, but what I did say is, this is how I stop the leakage. Can you do as well? Well, a few months, well, I better not say what happened a few months later. Right. This is something that we can also analyze. I'll go rather rapidly over the mathematics, but what I would say is that the results of our calculation are in good agreement with the experiment, the upstream and downstream extent. And the important question we ask is, what's the efficiency of storage? i.e., what's the volume that's retained in the current compared to the volume ejected? And the idea is that this volume injected varies linearly with time, so it goes on and on. And what we find is, both mathematically and experimentally, it goes down like t to the minus half, i.e., for a long time it all leaks out. And that'll happen in that case too. This is an indication of the efficiency as a function of time. Until it meets the fracture, the efficiency is 1, because all the fluid injected remains in the current. But then it begins to go down depending on the various parameters, and it can go down quite quickly. For Sleipner, as you see here, it depends how close the fracture is. If it's a kilometre away, then it takes a few hundred days for the carbon dioxide to reach that fracture, and then using sort of typical values, it goes down quite rapidly. Over 4 or 5 years, half of it would have escaped, which is not what you want. Now, of course, the parameters can vary enormously, and this is just an indicative calculation. No matter what the geometry is, whether it's two-dimensional, whether it's a point source and a sink, or whether it's a point source and a line sink, we find that the efficiency goes down to 0 with the time, i.e., if you keep on pumping it, you'd lose all of it if you didn't do something. On the other hand, postdoc of mine, or two postdocs of mine, Jerome Neufeld and Dominique Vella over the summer with a student from Harvard, looked at what happens if you have flow down a slope with leakage. And slopes are important because the best carbon dioxide experiment at the moment, carbon dioxide storage experiment, is in Australia, where they're putting carbon dioxide up a slanted horizon here. And the question is, what would happen if there was a leak here? Because some of it would go up and some of it would continue, just as you saw here. So now, rather than do an experiment and bring this down as well, I'll show you a movie of it. You see the input is here, the leakage is here. This is actually a rather simple situation to solve, because you see it's almost horizontal here, and here it's parallel to the base, and there you get a partial differential equation to solve that allows for the leakage, and you find for the first time, that, in this study at least, that the efficiency goes to some constant that's different from zero, i.e. once it's past the leakage point, no more will leak out. This is a comparison between theory and experiment that goes quite well as a function of time, again confirming the usefulness of the theory and the experiment. Now, what I'd like to do in the last 10 minutes or so is to tell you one other effect and then a few concluding statements. And the other effect I want to tell you is what is the effect of a heterogeneous permeability. Because the Earth is heterogeneously permeable everywhere, and the simplest case you can think of is to have a region of high permeability and a region of low permeability, and this seems to have, oh, there it is, a region of high permeability either below one of low permeability or the other way around. So just two layers, what will happen if you input heavy fluid at the base of it. Now, the important thing is that because it's heavy, then gravity will make it go downwards. But there's something called flow focusing due to larger permeability. Because it's easier to get through this permeable region, it will come to this state preferentially. Gravity makes it go down. In this case, it also would like to go into this layer, and so that's not very interesting. You get something that looks like this because the two act together. And it looks something like that. You have enhanced transport, and that's really important because the flow is focused in this lower layer. On the other hand, what happens in this case where they act in opposition, where you're putting in heavy fluid into this region? Because it's heavy, it wants to go into this lower layer, but because there is larger permeability, it wants to go into this upper layer. Well, I don't know what will happen, so let's do an experiment and see, and keep quiet. Yeah. Whoops. Is that not in anybody's eyes? That'll be sufficient. What I have here is some foam and some ballatini, little plastic balls. The foam is of relatively low permeability. The fluid doesn't like going through there, but the balls are of higher permeability. And what I'm going to do is some more blue-dyed salty water. I'm going to add it right at the bottom here. If I added it very, very slowly, this heavy water into this light, pure water here, very, very slowly, then it would be able to go through this foam and it would go away on the bottom. Well, let's see what does happen. Well, you see some of it is beginning to go through this foam, but some has already found it easier to go on the top here. Why does this not show as well as the others? Can I? Ah, that's better. Yeah, if you could make it closer in. Thank you. You see here, I mean, I can see it clearly. I hope you can. You could all come up on the stage and give the lecture. Yeah, that might be a good idea. Here is the fluid going across. But now, you might say, well, what's so interesting about that? Well, the interesting thing is this is heavy fluid, heavy salty water above light salty water. Now, how does that happen? It just nicely propagates across. And it does that because the permeability here is larger, and it's easier for it to go across there. Because I added enough. If I'd added just a small amount, it would have gone here. Well, just in case the experiment didn't work, I had a photograph of it. That's what you're seeing. And I'm going to leave out again some mathematics and say that in the end, it must start looking like this, because the heavy fluid must go down, and because it's heavier. But this shows that the carbon dioxide, when it meets different permeabilities, can really propagate in a quite different way, and a way that we'd have to calculate, because it is important, if we're going to get this system going, to be able to know just how far the carbon dioxide would spread. Well, there are lots of additional facts that I could tell you about. I could tell you much more about heterogeneous permeability. I could tell you about chemical reactions between the carbon dioxide and the hot rock, because the rock is considerably hotter a kilometre down. I could tell you about convection, which may be driven either by thermal effects, or much more dangerous, by dissolution of some of the carbon dioxide as a gaseous phase. And we know that there are very strong volcanic eruptions due to the release of gaseous material. Can't find the way to. I've already talked about dissolution, but there's still a lot of work that can be done there. And it would be fun to talk about mineralization, and a colleague of mine has just written a paper on mineralization. But as I say to you, that's going to take a very long time. Is there enough space for us to put this carbon dioxide? I don't have the figures for Europe, but I do have for the United States, where the 7 largest areas were evaluated for billions of tons of carbon dioxide, the maximum value and the minimum value. And so the idea is that there's something like 3,631 billion tons of storage capacity. And I like the way they give you this result to 4 significant figures. It gives you great confidence in what they would do. This is something like 500 years of storage capacity for the United States. So it's even a few hundred years in the minimum event. Now, this I think is a very sad indication of the world and the current sequestration projects. There's, of course, a lot going on in America, a lot going on in Canada, in Australia. Otway is, I think, one of the best projects at the moment, storing something like 700,000 tons. The Gorgon project, it's about to start up, but nothing in South America, nothing in most of Southern Africa, nothing in Russia, nothing in India, nothing in this region here. And my belief is, first of all, that carbon dioxide is not going to be transported large distances. It's too expensive to do that. It's going to be stored more or less where it's created, and that it's important to have local knowledge. And there's no local knowledge being generated here, none here, none here. And I think that's a problem. Well, finally, if I can add some conclusions. Global warming is probably occurring with large worldwide consequences. That's really the point I wanted to make at the beginning. Fluid mechanics is my subject, so I've tried to show you how it can play an important role in the question of carbon dioxide sequestration. We've used data from Sleipner and found that models that we can understand give us greater insight into what's going on there. It's important that we can quantify and understand the rate at which the carbon dioxide might be dissolved into the surrounding salty water and made heavier, but leakage through a fracture can be substantial, and we need to know about that, and we need to know how to stop that happening, to come to a process that I believe is really very important, has a vital role to play in our future, and I think this is an important point, can be as large as the oil industry and just as profitable. Finances play an important role, but it does need the government to take a very active role. Well, thank you very much. Do I stay up here or?
Thank you very much, Herbert. That's a wonderful lecture. I think you're prepared to take a few questions?
No.
No. Well, we're going to have some questions anyway.
Okay.
That's all right.
I like being in control.
Well, may I say, if there are a few questions, and we have a limited number of questions, there are some roving microphones, and if you could stand up when you ask your question and speak into the microphone when it arrives. So if there are any questions. One. If you could stand so the cameras can see you.
Thank you. Thank you very much. Do you accept that there is only any practical point in anything you've said this evening if human beings control and in actual fact reduce their number on planet Earth? And I would extend that question to any attempt to alter the form of energy production that we use, whatever it may be, or any other impact we have on the environment.
Well, I'm glad we started with such a simple question. You don't really want me to comment on the population of the Earth, do you? Yes. It doesn't come into the fluid mechanical equations or mathematics. I think that is a very interesting question. And if I'm awarded the Bakerian lecture next year, I'll give you a long lecture on it.
Other questions?
You've convinced us that you can do a lot to store carbon dioxide. You haven't said anything about how you capture it in the first place from where it's being generated, and you didn't say anything much about the economics of doing this compared to, for example, putting the same amount of money into building nuclear power stations.
Well, I did make a comment of nuclear power. I think the public is not going to be very receptive to that idea. You capture the carbon dioxide by chemical means from where it's produced at the power stations is the most obvious one. And that is quite well understood, and the belief is that the cost of that is going to decrease by about a factor of 5 over the next few years. Cost is an interesting question, and people frequently say, where's the money going to come from to store the carbon dioxide, to put into place these extra processes? And the point that I would make is if we look at something like gas prices for, petrol prices for cars, quite clearly we're willing to pay extra amounts, and in this country we pay quite a lot more than in America, but I haven't noticed that people are not driving cars. And I think that extra cost of sequestration will just be added on to the cost of power, electricity, petrol, everything. And we'll just shake our heads. And Bob Watson is agreeing with me, which is wonderful.
Thank you, Bob. We have two more questions, one here and one there. Yes, first.
I'm amazed that you're against nuclear power. Another point. No, my question is, what about burning fuel underground? It's in the spirit of what you're doing. Is it in any way a competitor? Underground gasification of, coal and such like?
Well, first of all, let me say, I didn't say I'm against nuclear power. I've never smoked a cigarette in my life, but I could say quite firmly that smoking is prevalent. Michael, is that not right? And I've never smoked in my life. So I'm in favour of nuclear power, actually, but I don't think the public is in favour of nuclear power. And I think that's quite clear. Now, burning things underground, what do you then do with the released carbon dioxide? If you burn it a few hundred meters underground, you still have to pump it down to a kilometre at least to get it in its supercritical state. That doesn't change much, but the cost, and I'm not an expert in the economics, but the cost of having the power producing plant underground has to be added on to that.
Okay. One question. Another question here.
Congratulations on a lovely lecture. My question is now about the lecture, not about the politics surrounding the lecture. Presume you showed elegantly, as we know, that carbon dioxide can become supercritical. And am I right in assuming that the experiments and so forth are germane to a brine solution saturated with carbon dioxide? So when you said carbon dioxide underneath, you didn't mean carbon dioxide in the gaseous form, did you? You meant brine saturated with carbon dioxide.
Well, it comes off in the gaseous form, and then what you're doing by bringing it down below 800 meters is putting it into the supercritical state. You're compressing it so that it takes very much less space.
Yes, I see. But so what is the relevance then of the brine? It was just a means of getting it down there.
No, the brine is there. You're putting it into storage space. What are the best storage spaces? I think I tried to say that some way through the lecture. You could put it into the porous medium of bad coal seams. You could put it into depleted oil reservoirs, but by far the largest storage space is saturated brine water. The porosity might be 10% or something like that, but the rest of it is taken up with salty water. And could I also just thank you for your kind comments and point out to the audience, this is a previous Bakerian lecture who...
We have time for one more question. Give me the microphone, please.
Dan, there's a microphone there.
I have read that if all carbon dioxide that is currently being emitted were reduced to zero today, the loading of carbon dioxide that is already in the atmosphere means that temperatures will continue rising for at least 100 years, suggesting that the real solution probably needs to involve extracting carbon dioxide from the air or from the atmosphere. Can you comment on the feasibility of that?
Well, you raise an important point, Dan. The residence time of carbon dioxide in the atmosphere is many, many decades, maybe up to 100 years. And so even if we stopped producing carbon dioxide now, which is impossible in my opinion, there would still be an influence for quite some time. That's why I think we have to store it. To take it out of the atmosphere, because in some sense there's rather a small amount, it's only 400 parts per million, is a very expensive process. It's much better to store it or to take it and store it at its initiation point. One final thing I would like to say that's partly in answer to your question is why I think this is such an important problem. I think it's the first global problem that the world has ever experienced. In the past, if there were terrible pea soup fogs in London, nobody in Paris cared less. But wherever we put carbon dioxide into the atmosphere, because of the winds, it propagates over the whole world. And if we, i.e. Britain, suddenly stopped putting carbon dioxide into the atmosphere, that wouldn't help matters because China and India and the United States still are. It's a global problem. My belief, and I'd love to hear a counterexample, is we've never faced a global problem before, the world, and that makes it different to any other problem we've had to investigate.
Yeah, the stratospheric ozone depletion. We put chlorine and bromine compounds in, so it's similar in that, but much less economically important, but that was a global issue as well.
And that was solved so quickly.
For a couple of reasons. First, basically, the implications was more ultraviolet radiation at the Earth's surface, giving cancer to light-skinned people, and cancer is probably the scariest word in the dictionary, so people immediately wanted action in the US and in Europe. Two, we found some really simple substitutes, and it didn't have a macroeconomic effect.
Yeah, it was not very costly, and it was relatively easy.
Well, I think we've reached the witching hour, and it remains for me to thank you, Herbert, for a fantastic lecture. In particular, I think I should stress, running live experiments in a lecture is one of those great challenges and proof you can actually see it happening in front of you. It's remarkably bold and is, of course, also in the great tradition, Herbert, so we thank you very much for that. Also, thank you for addressing an extremely complex problem. You've explained the complexities involved in it, and also the open rigour of the science that underpins it, which is actually what gives everything the confidence and credibility to step forward in the way we have to. Well, it remains only for me to actually, I think, make a small presentation. I think they may well actually be sitting here, Herbert. Yes, I have them all here. There is a scroll. Thank you very much. A cheque. I don't think it's £100. And a medal. And I think on that note, we thank Herbert for a fantastic and wonderful 2011 Bakerian lecture. Herbert Huppert.
Thank you very much.